Let's continue this review of basic logic gates. Same thing, information chapter number 3 and chapter number 2 PDFs provided on Canvas. And we just went through the different types of logic gates that we can have, 7 basic logic gates. And we know that we can use them to implement some arithmetic, some addition, for example. Now let's look at truth tables. So the operation of any logic gate or any Boolean expression can be described by a truth table. And we have here 2 examples. Both of them have just 2 bits, but this one has 1 output, this one has 2 outputs. So we organize the inputs and the outputs, and we also represent the patterns here based on 2 to the n, where n is your number of bits. If I have 2 bits, I need to have 4 patterns. And I need to also indicate which one is the least significant bit and which one is the most significant bit. So the most significant bit is represented to the left, to the far left of your truth table, and the least significant bit is going to be the one to the further right of your inputs. We also have an additional state called don't cares, and there are different ways of representing that. We can either use an X or a dash. And what does it represent? It denotes exactly does not matter. And next week we'll cover a different way of organizing our Boolean expressions or reducing our Boolean expressions, and don't cares are going to be very useful for that technique. For now, just have in mind that I can have a bunch of X's or dashes either on the input or output of my truth tables. Why are truth tables important? It's another way or another layer of understanding and serves as a starting point in a new design. So let's go over the buffer. This is a truth table for the buffer. So notice that it's just a triangle. Whatever I have on my input shows up on my output, and it minimizes the effect of the noise on a line by acting as a digital amplifier. So it just guarantees that you have somehow current being amplified from one point to the other, but does not alter the values of that line. The pinout, the IC, if I want to use this, is the 7407. They're different manufacturers. And notice here that I have 6 different buffers inside of this IC, but I always have a VCC and a ground. So I always need to supply ground and VCC to this IC in order for the rest of the elements to work properly. And then I have the input, output, so forth and so on. This is the Boolean expression. Your output is equal to your input, A. Alright, Boolean expressions describes in algebraic terms the behavior of the gate. It was invented by George Boole, and notice here the dates 1815 to 1864. So it's pretty old stuff that we're using here, but still relevant to today's technology. Let's go over the inverter and the Schmidt trigger. So the inverter operates different than the buffer. In this case, it's going to invert the signal. If my input is a 0, I get a 1, and vice versa. The famous IC of NOT gates are the 7404. So again, you have a VCC and a ground and 6 NOT gates inside with the respective input and output of each gate on that IC. And the Boolean expression is the negation that it's done with a dash on top of the letter. Often it's necessary to square up a signal for use by a digital circuit, and the identity or the circuitry responsible for that is called the Schmidt trigger. This is just a representation. So imagine that I'm feeding an analog signal on this digital circuit here, this TTL, and the problem here is that whenever I have values between these 2 volts and 0.8 volts, this is an undefined region that I don't know if it's a 0 or a 1. So what happens is that if I have a Schmidt trigger, this is an inverted Schmidt trigger because I'm inverting my output. Notice that these are the levels that we just saw, and whenever my input is on this level, the output switches, but it's not bouncing like crazy. It's just either 0 or 1. It never goes under this undefined region over here. So Schmidt triggers, you're going to find these a lot to make sure that your signal is 0 or 1 at the entrance of your gates. This is an example here, another one just showing you the output visualization of waves. If I have this sinusoidal wave, I get this square wave. Let's go over the AND gate. So the AND gate, this is the symbol, this is a truth table. For all the possible patterns that we have here are 0 besides or except the last one. So all inputs need to be 1, so you can get a 1. And you get these IC, the pinout, the 7408 with VCC and ground. Notice that I have less gates inside because now I have 2 inputs instead of 1. So I'll have less space inside of the IC. And the Boolean expression, F equals to A and B. Different ways of representing that multiplication, but we're not going to use any of these because this can get confused to the inner and outer product. So we're going to use the AB. Sometimes we put the dot, but let's just keep it simple for now on the slides, and I always keep it like this for AND gates. We can have 3 inputs. For 3 inputs, so 2 to the power of 3, I get 8 patterns. This is my truth table, and it's only 1 when all the inputs are 1. This is the IC, and this is the Boolean expression, F equals to A and B and C. Let's go over the OR gate. This is the symbol for your OR gate. It's 1 in all combinations besides the first one when it's 0. This is the IC. This is the Boolean expression. For OR gates, we use an addition. Don't get confused with binary addition. All right, this is different. This is gate addition. 3 inputs. And this is my truth table now. All ones besides the first one. F equals to A or B or C. And if I don't have these IC available, if I only have the 2 gates available, I can always represent or design this 3 input gate as 2 input gates. This is true for any logic gate. So this has the same behavior as the one on the top here. Let's go over NAND and NOR gates. Your NAND is your AND negated. It's like an AND with a NOT in front. So what's going to do is going to invert the output of your AND. So your AND was all zeros and 1, but now I'm negating, becomes all 1s and a 0. This is the famous 7400 IC for NANDs. And now the NAND, if I'm negating the output, I put that negation on top of A and B. This is a NAND gate with 3 inputs. Same thing applies here. Same thing for your Boolean expression. But now let's be careful with one common mistake that students do at the beginning when they're learning these logic gates, which is confusing negating the inputs of your AND gate, saying that it's equal to negating the output. And that's not true. So if I negate the inputs of the AND, this is not the same thing as having the AND and negating the output. Careful. If I put the truth tables here, notice that this truth table is completely different than this truth table. So do not make this mistake. This is not true. Then we have our NOR gate. It's your OR with a negation in front, or your A or B negated. Same thing applies for your NOR gates with 3 inputs. And same thing applies here. Mistake. We go to our NOR gate and we say that negating the inputs is the same thing as negating the output. Completely false. These two statements are not related. Look at the truth tables. Completely different. And at last, your exclusive OR or exclusive NOR gates. So this is your exclusive OR. This is your summation in binary. So notice here that 0 plus 1 gives you 1, 1 plus 0 gives you 1, 1, 1 gives you a 0, and I'm not representing the carry. So the exclusive OR is doing the summation of binary numbers all the time. Or if you want another way, probably easier way, is if you have an odd number of 1s, you get a 1. If you get an even number of 1s, you get a 0. And the Boolean expression is A exclusive OR B, or I can represent these also just with AND and OR gates and NOT gates, which is the same thing as designing this circuit over here. This is an exclusive OR with 3 inputs. So notice here that if I have an odd number, I get a 1. So odd numbers, 1, odd, odd, 3, now 3 ones, odd number, and I get a 1. And then at last the exclusive NOR, which is the negation of your exclusive OR. So it's the inversion, or if you want, for odd numbers you get 0, for even numbers you get 1s. And as you're expecting, you're just negating the top of your exclusive OR, or the same thing as having AB or A0 and B0. This is an exclusive NOR with 3 inputs. And just a practice here, how can I decide the exclusive OR gate with just OR and a NOT? We just saw it. So if I have this is going to be my exclusive OR just using AND, OR and NOT gates. And if I design, here you go, I get this first one, A and B0 is this part over here, which you get your A and B0. And then this part, this second term is your A0 and B, which is this part of the circuitry. And then you're doing an OR of the result of this AND and this AND, which is this part over here, and you get your final circuitry. How many gates do I need? 1, 2, 3, 4, 5 gates using 2 ANDs, 1 OR and 2 NOTs. What's easier to use, 1 exclusive OR gate or 5 logic gates? So logic optimization is important in order to reduce the number of logic gates in a digital circuit, and that's what we're going to spend time this week and next week, kind of massaging the circuit so you can have the most or the simplest circuit possible.